Hello and welcome to the YouTube channel of Canara Engineering College. In today's video session, we'll check regarding the design of binary up-down counter. So till now, what we have done is we'll just brush up the things what we have studied till now in case of your counters. So what we have done till now was we have studied what are counters. We have checked out what basically is a counter, how does it work, what are the components that in fact build up the counters, and what are the different components that can be used to build the counters. Later we studied the types of counters. We have studied the various types of counters. Once these types of counters has been encountered, we have studied regarding the design. So when it came to the design of counters, we studied the design of asynchronous as well as synchronous counters. After the design was done, we studied in detail with respect to your synchronous counters or synchronous up counters. So in the synchronous up counters, we have studied the design with respect to your T flip-flop and D flip-flop. So both the flip-flops, whatever we have taken, were helping us in the design of counters. And the counters what we have designed here are all synchronous. I mean to say the same clock input will be given to all the counters as well as the counters what we use here or whatever we have designed are up counters. In fact, it is possible to design even down counters. The changes what I need to do when I'm designing down counters is the table whatever I was writing here should be changed. That is, if we go back, that is when I'm writing this particular table, what you need to write here is, for example, if you are designing a down counter, you need to be writing the first number as 1, 1 and 1. The next number will be, obviously it will be, what is the next number? It's going to be 1, 1, 0. The next it is going to be 1, 1, 0 here, and the next number here is 1, 0, 1. So here you are going to write 1, 0, 1. The next number here is going to be 1, 0, 0. After 1, 0, 0, you are going to write, what will be the next down number? It is 0, 1 and 1. So here you are going to write again 0, 1 and 1. After 0, 1, 1, you are going to write, what is the next number you are going to write? You are going to write 0, 1, 0. This is how you are going to write the table of the present state, next state and the flip-flop inputs for your down counter. So you are starting from the higher number and you'll be going in the downward fashion. But the number of flip-flops whatever you are going to take will remain the same whether it is a up counter or it's a down counter. Maybe when I get the equations for dA, dB and dC, this equations might change. Whereas in case of your up counter, we got it as A XORed with 1. Later you got it as B XORed with A. And last one you got it as C XORed with AB. You got this particular equation. Maybe if I am designing it for a down counter, the equations what I obtain here might change because the values whatever you are writing here and the values what it is going to be filled up in the flip-flop input table is going to change, which ultimately is going to change the K-map what you are going to write at the end and obtain this particular equation. So once this equation changes, the design will also change. So that is with respect to your down counter. So these are the things what we have done till now. Now the question is, sir, is it possible to design or is it possible to go with up counter and down counter together? Is it possible to have one single circuit and is it possible to count from 0 to, for example, 8, and after that I want to count from 8 to 0. So I mean to say, is it possible to design an up counter and down counter in the same circuit? The answer to this is yes, it is possible to design. You can design an up counter and down counter in the same circuit. Maybe there are some additional inputs which needs to be given to this particular counter, but in spite of that, you can design a counter which will be counting in the upward fashion and downward fashion in a same circuit. The diagram what you can see here, this is a state graph or state table for a up counter and down counter. So this basically has got how many counts? 0, 1, 2, 3, 4, 5, 6, 7. So this basically is a mod 8 counter because it has got 8 counts, right? So if you check out here, this is the first state. This is the first state of your counter. From the first state of the counter, it goes to the second state, which is the next number. From the second state, it goes to the third state, which is the next higher number, which means your counters moving from 000, it is going as 001 up till 111. After 111, it is getting back to 000. So if you can check it in clockwise direction, you can see the state table is indicating that the count is progressing in the upward fashion. Similarly, if you can check it in the anti-clockwise fashion, from 000, it is going to 111. From 111, it is going to 100. See here, this is your first number. Or you can consider this to be your first number, and this to be your second number, or this one to be your third number, which means your count is going in the reverse direction, or it is progressing in the reverse direction, and this is the state table or state graph for your down counter. As it is a design of up down counter, what we have done is we have taken a single state table, and in one single state table we have designed up counter as well as down counter. And the table what you can see here, these are the inputs or the flip-flop inputs or the states of the counter which occurs when the count is going in the upward and downward fashion. See here, this is your first number. Let's say this is your first number. First number, second one, third, fourth, fifth, sixth, seventh, and eighth. So 8 counts. So here you can see after 000, it is going to be 001. After 001, it is going to be 010, which means that the count is going in the upward fashion. Always what you can do is, if the count is progressing in the downward fashion, you can check here. If this is the initial state of the flip-flop, the next count what your counter is going to count is 111, which is the highest count what it can display. After 111, it is going to count 000 again. After 000, it is going to count 001, which means that this is counting in the downward fashion and this one is counting in the upward fashion. The same thing whatever I have drawn in the state table or state graph has been indicated in the table here. This is all it has been done here. Going on to the design of this particular binary up and down counter, if you design the things as per the table what you have drawn, you have already drawn it for a up counter, you have already drawn it for an up counter. So let's recall back the equations what we have obtained there. So the equations what we got there are dA is equal to A XORed with 1, right? dB is B XORed with A, and DC here is D XORed with AB. This is what equations what we have obtained for an up counter. If you have got any doubts, we can check it out here. You can check it out here. So the design of the up counter, whatever we have done with respect to the D flip-flops, has given me this equation. This is actually A XORed with 1. This is B XORed with A. This is C XORed with AB. The same equations has been written here. The same has been written here. Suppose if you are going with respect to your down counter, suppose if you want to get an equation for down counter, it is not necessary that you need to design or you need to write those particular tables input to the flip-flops, and it is not necessary that you got to get the equations for the down counter separately. What you can do is you can just write equation for dA to be equal to, say it's given here. The equation for dA is given as A XORed with U or D, which where U stands for a signal in the circuit if the counter has to be counting in the upward fashion, and D stands for the signal in the counter which counts in the downward fashion. So you can check the circuit here. We'll get back to the circuit again, but with respect to this U and D, I'll show you where this particular signals are present here. So you see the signals. It's U here, it's U here, and it is U here. So basically U and D are the input signals. So what I can understand from this is, what I can understand from this particular signal is, if you want your circuit to be counting, or if you want it to be operating as an up counter, you need to make your U signal as 1 and you need to make your D signal as 0, which means that U signal is activated. If you activate U signal, your circuit will be counting from 0 to the count what you have specified. Very similarly, if you want the circuit to be counting in the downward fashion, you need to be making your D signal high and you need to be making your U signal low. So if you are doing this particular changes in the circuit, the circuitry what you can see here can function both as up counter and down counter. But you people need, or the user has to specify what is it has to perform as, whether it is an up counter or down counter. If it has to perform as an up counter, the signal inputs where it is showing as U should all be connected to high, and D signal where it is seen in the circuit should all be connected to 0. Very similarly, if it is down counter, it will be in the vice versa fashion. So let's take this circuit, let's take this equation, let us take this as base equations. The equations what I have here, let us take them to be the base equations. So let me say I want it to be performing as an up counter. When it is performing as an up counter, what do you do here? You make your U equal to 1 and you make your D equal to 0. So when you make your U equal to 1, it will become 1 or 0. So that will in turn become A XORed with 1. A XORed with 1 will be A bar. So DA will be A bar. Very similarly, if you want the equation for DB, you need to be making this D equal to low and you need to be making U equal to 1. So what is this going to become? This will become B XORed with A. Very similar to the previous thing what I obtained. This was the equation what I obtained for up counter, right? Very similarly, if you want it to be performing as an up counter, let's check the equation for DC. So this is a base equation for DC where D has to be made low. When D is made low and when U is made high, it will become C XORed with AB, which is the same equation what we have obtained previously. In case if you want it to be performing as a down counter, let's say that, sir, I want the same circuit, but the circuit what you have used it as an up counter should be performing as a down counter. That is, it has to be counting from higher number to the lower number. So here what you need to do is, you need to be making U equal to 0 and D is equal to 1, what has been explained here. So when you go to this particular equation here, U is 0, D is equal to 1. So that will be remaining the same. That will be A bar itself. Very similar to the equation what we had previously. Coming to this, U is made 0 and D is made 1. So it will become B XORed with A bar. So it will be B XORed with A bar. Finally, the equation for DC will become C XORed with B bar A bar. So you can see the changes in the equations. You can see the changes. If it is working as an up counter, the equation is given here. And if it is working as a down counter, the equation is given here. The equation has been given here. The circuit diagram with respect to that has been rigged up here. So the circuit what we had previously, that same circuit has been modified as per the requirements. And when you want it to be acting as a down counter or up counter, you just need to take care of the signals U and C or U and D. So if it is an up counter, you make this 1 and you make D equal to 0. Suppose it's a down counter, you make D equal to 1 and you make U equal to 0. So this is how it has to work, or this is how you actually design an up down counter using a same circuit. So the flip flops whatever you have taken are the same numbers. So you have 3 flip flops, you have got data inputs, you have got clock inputs, everything remains the same. But only change here is 2 additional signals are added to the circuitry with some additional gates. This additional gates will make sure that the circuit what you have rigged up here, or the flip flops what you have rigged up connected here in order to form a register, will be acting as a up or down counter based on the requirements. Moving on further, the topic says here loadable counter. So it's the same counter what we had here, but the change here is, what we need to do is, you can load the values to the counter. Loading the values to the counter says that, for example, let's say that it is a mod 8 counter. It's a mod 8 counter. let me say that I normally my count will be starting from 000. This is where it counts and it goes up till 111. Let me say that I want my count to be starting from 110. I want it to be starting from this particular number. And later it has to go to 111. Later it should be 000. Later it should be 001. I mean to say that the first count what your counter is going to show, I want that first number to be as per my requirement. So the sequence what has to be counted in the counter will be loaded by you people, and later my count will progress from that particular state. For example, if you have loaded the number 110 to the counter or to the flip-flops what makes up the counter, it is going to count from that particular number in the upward fashion or in the downward fashion as per your requirement. That is what is called as loadable counters. Loadable counters are basically the counters to which you can load the first count. First count can be loaded to that particular counter. So that is what it is all about. And when you, if you can see the symbolic diagram here, you can see everything is normal. It's a normal flip-flop here. It's a 3-bit counter or it's a 3-bit register. It has got a clear signal. It has got a clock input. It has got 3 inputs. It has got outputs. So everything remains the same. The additional inputs what I can see in the loadable counters are, one is count and other one is load. Very similar to what you saw in the up and down counter, you had two additional inputs, right? Up and down. Very similarly, loadable counters will be having two additional inputs. One is count and one is load. When load is equal to, please understand this very carefully. When load is equal to 0 and when count is equal or load is equal to 1 and count is equal to 0, whatever data you are thinking of loading to the counter will be loaded to this particular flip-flops. For example, let me say I want to load the value 110. So what you will do normally, you will clear all the data in the flip-flop. After that, you will keep the data 110 at the data inputs of the flip-flop, and you will make load equal to 1 and you will make count equal to 0. After that, if you make load equal to 0 and if you make count equal to 1, the count of this particular loadable counter will start progressing in the upward fashion or in the downward fashion as per the design what you have carried out. So if this is an upward counter, or if it is an up counter and the number what you loaded is 110, the next count what it is going to display is 111 with respect to the clock input what you have given. Suppose if you make load equal to 1 and count equal to 1, suppose if you make load equal to 1 and count equal to 1, then which one should be done? Whether the count has to be progressed or whether the number has to be loaded. My load signal will override the count signal, which means that when both the inputs are high, it is possible to load new data to the counter, whereas the count cannot advance further. Even though both are high, my load signal is stronger than the count signal, which means that load signal will be overriding the count signal. Suppose if load is 0 and count is 0, then your counter is going to display the same count what it had previously, which means that no change in the count will happen. That is what this particular loadable counters are. You can see here, there is a load signal here and there is a count signal here, one here and count signal here. And also you can see there is a load signal here also. It's a load signal which is connected to the mux. Can you see that? It is connected to the mux with the data input to the flip-flop, isn't it? So that is what I said. When load and count both are equal to 1, when load and count both are equal to 1, if you're asking me, sir, how does this load override the count? You can see the same load signal here. You can see the same load signal here. So this load signal will make the data that is present here to get loaded to the flip-flop what it is connected here. Basically from here nothing happens. Basically from here there is nothing happening. Only thing from where the data will get loaded to this particular flip-flop is through this particular multiplexers. So the additional thing what I can see here is I have rigged up a loadable counter with a multiplexer, where your load signal can override the count signal when both are equal to 1. And this overriding can happen because the load signal are present in 2 points of my circuit. One is along with the count signal it is present. One, the same load signal is present also in the multiplexer. So when both are equal to 1, the data from the multiplexer will be getting loaded to the registers or to the counters it is present here. Later, if you make your count equal to 1 and if you make your load equal to 0, then the counters will start counting in the upward fashion or downward fashion as it is required. So these are the two important topics what we'll be covering up in this video session. So one was up down counter, other one was load counter or loadable counter. Thank you.